Good morning, good afternoon or good evening from GFoRSS TV. GFoRSS TV. Today, on GFoRSS TV. Coming up next, on GFoRSS TV.
Hi, my name's Simon Hurd. Welcome to the next stage of our training on Commission Implementing Regulation 2021-808. Today we're going to focus on the details about how to validate a confirmatory method. After a brief introduction, we're going to show you how to evaluate the required performance characteristics. So we're going to cover some general characteristics, the trueness, repeatability, reproducibility, and CC alpha. We're going to look at some case studies to show the differences between validation batch design for approved and banned substances. We're going to focus on the calculations and interpretation before summarizing. A quick reminder on validation. Validation or method validation is the process of proving that an analytical method is acceptable for its intended purpose. And validation is a requirement for ISO 17025 and is typically undertaken before the method is implemented in routine analysis. The performance characteristics that need to be verified for Commission Implementing Regulation 2021-808 vary depending on the type of method in place. And here we're really just going to focus on confirmation. And Commission Implementation Regulation 2021-808 focuses on a single laboratory in-house validation approach. This slide shows the experiments, the parameters that need to be tested for and evaluated as part of validation of a quantitative confirmatory method. The first thing to remember is that the results need to comply with the requirements for a confirmatory method, including identification criteria. We then need to calculate decision limit, CC alpha. Note that we don't need to calculate CC beta anymore for confirmation. It's now primarily just a screening tool. And we need to then calculate trueness, precision, relative matrix effects, absolute recovery, specificity, stability, and ruggedness. We also need to consider the relevant sample types to be tested because we need to validate them separately. So for example, if we have liver, kidney, and muscle, we need to carry out separate validation because these samples are very different in the composition. We need to consider any other relevant matrix, such as, for example, for testing live animals, such as urine, blood, or hair, and any products of animal origin that may be relevant as well, so things like milk, eggs, and honey. We also need to consider the species of the animal being tested. I think when you're starting out with this process, initially doing the validation, it's important to validate the species separately. And if we find the results are the same, then you're justified in future validations, future routine measurements to combine the species. We also need to consider the type of quantitation calibration that's in place as well, as this impacts the requirements. For example, we only need to look at absolute recovery when no internal standard or matrix fortified calibration is used. So as we showed on the previous slide, there is a lot of work required to validate a confirmatory method, and we want to try to minimize the workload. So it is possible to combine some of these experiments. We can assess calibration graphs. We can then calculate trueness, repeatability, reproducibility, and CC alpha from a single validation data set. The big difference is the concentration of the spikes is dependent on the type of level of interest, so an MRL versus a banned substance. In my opinion, initially, especially when you're starting out, most other experiments are best dealt with separately. So I'm talking about ruggedness, specificity, absolute recovery, relative matrix effects, and stability. And convenience, just for convenience sake, we're going to take those first. Ruggedness is where we introduce minor changes and variations deliberately into the methodology. There's no fixed criteria in a document. It just says that the importance of the changes should be evaluated. So what sort of changes could be considered as ruggedness? With my opinion, it's when we're first starting out with these types of approaches, change the analyst doing the work, change the person running the instrument, change the instrument. I think these are good examples of ruggedness. What tends to happen is you become more confident and more familiar with these processes, then these types of changes are included within laboratory reproducibility. Other areas that are key to ruggedness is looking at different grades or brands of the reagents, your materials that you're using. There's a lot of logic in this because you don't want to be reliant on validating purely on one supplier or one part number, just in case they run out. Similarly with an HPLC column or a GC column, we can look at different lots of the same product, or we can actually even look at the same type of column across different types of manufacturers. And also a critical aspect of ruggedness is where we modify the procedure in some way. So for example, if we're carrying out solid phase extraction, if we change the pH a little bit or change the proportions of the mobile in the pH in the mobile phase, or the proportions of organic versus aqueous, these types of small modifications, do they actually cause any significant difference to the results? And also even looking at the sample itself. So for example, different species, or even within a species. So is the method rugged enough to deal with lots of different types of fish? So we got white fish, we might have oily fish. Does the method work just as well, regardless of which type of fish you choose? This slide shows an example of testing the ruggedness of a method. So we've got a test for a particular substance spiked into a sample at 0.05 nanograms per mil, and we've done this a series of replicates. And what we're interested in is to see whether the results vary between the samples. And what's different in the samples is different fat content in the milk. And we can see from the graph that basically the results are not statistically different. So therefore we can be sure that our method will cope with lots of different sample types of milk. Specificity is defined as the power of discrimination between the analyte and any closely related substances. And there are two scenarios that we need to look at. The first is where there might be a component or components coming from the matrix, co-extracted out of the matrix, which may interfere with our analyte, measurement of our analyte, or there actually might be other analytes that we are testing for, which might interfere. So for example, if we're looking for one specific sulfonamide, we need to be sure that other sulfonamides in the method, in the sample, do not interfere with our measurements. So what we're looking for is to actually establish whether we can see any possibly interfering substances. There is no fixed criteria in a document. This is the type of experiment that we would need to carry out. If we want to look at the material coming from the blanks, then we basically run the method on the blanks, 20 blanks from different samples, different origins, different species, different lot numbers, different batches. So this is not 20 replicates of the same blank. We want to introduce as much diversity into the sample type as possible. And then we just simply look for the presence of a peak that could be misidentified or misdetected as our analyte. And then the other experiment we would do is we would take a representative blank sample and we would spike with lots of different substances that could possibly interfere with the identification or quantification of the analyte. So these are some results from the first experiment. So here we've got a series of chromatograms running a method for N-rofloxacin, and we want to assess whether we're getting any peaks at the retention time on the transition for N-rofloxacin. And we can see from the chromatograms that we have complete absence. So we can be quite certain that we have no interference. So therefore it is the method is rugged is specific. On the other hand, if we want to look at different other analytes, so we might have, this is our particular target analyte. We're looking at that zone here, and we can see our transitions we're looking at. And then we basically want to just check that there might be some other structurally related compounds. We just want to make sure that they do not generate a peak at the same retention time on the same transition. The determination of absolute recovery is a new addition to this regulation. Absolute recovery is the proportion of the analyte remaining at the point of the final determination following its addition immediately prior to extraction, and it's expressed as a percentage. The absolute recovery of the method shall be determined when no internal standards or no matrix fortified calibration is used. So this is testing how much we lose of the analyte during extraction or cleanup. The regulation goes into a bit more details. It states that the absolute recovery should be calculated for at least 6 representative lots of the matrix. An aliquot of the blank matrix should be fortified with the analyte before extraction, and a second aliquot of the blank matrix should be fortified after sample preparation at relevant concentration levels and the concentrations determined. And it gives us an equation to assess the absolute recovery. Matrix effects, and specifically relative matrix effects, are another new addition to the regulation. In general terms, the matrix effect is the difference in the analytical response between a standard dissolved in the solvent and a matrix match standard, i.e. a standard dissolved in a blank extract. This is important because this type of difference in response can have a huge impact on our accuracy of our method, so it needs to be evaluated at validation. The regulation calls out the relative matrix effects, and it defines this as a difference in analytical response between a standard dissolved in the solvent and a matrix match standard with a correction using an internal standard. So we have a typical scenario. We have chloramphenicol. We have two transitions for chloramphenicol, and then we have a response from the internal standard, chloramphenicol D5. Regulation provides more details about how we go about testing for the relative matrix effects. It talks about taking 20 replicates of the standards and then calculating various parameters using the peak area from the matrix match standard and the solvent standard and the internal standards, as we can see on the slide. It also gives us a RSD value that should be not greater than 20%. The one thing that's confusing about the regulation is it's not clear whether matrix effects need to be assessed in the absence of an internal standard. The regulation refers to this relative matrix effects, and it always includes the internal standard in the calculations. However, it is always good practice to assess the matrix effects regardless. So the matrix factor could be calculated by a comparison of the slope of the calibration series prepared in the solvent and in the blank extract. So we can see on the right hand side we have two graphs. We have one graph with a line through it, which is being prepared in matrix, and then we have the other graph which has got no line through it, which is being prepared in solvent. And we look at the slope of those two graphs to give us the matrix effect. But just as a reminder, this is not part of this regulation, but it would be good practice to assess the matrix effects regardless. Analyte stability is one of the most critical aspects of analytical quality control and validation, and yet it tends to get forgotten. The stability of analytes in the calibration standards, whether it be in solvent, matrix matched, or matrix fortified standards, and also in the sample, either during storage or during analysis, needs to be determined. Usually, the analyte stability is well characterized by the vendor, the supplier of the analytes, reference material that you have purchased under different storage conditions, or there may be information in various peer-reviewed publications. So if you use the same storage conditions, it may be possible to use that stability data. Commission Implementing Regulation 2021-808 provides very clear instructions on the determination of analytes, stability of analytes in solution, and also stability of the analyte in matrix. We're going to now move on to looking in more detail about the design of validation plans, the so-called conventional approach. So just as a reminder, for the design of the study plan, we're going to cover trueness, repeatability, reproducibility, and CCL from the same validation data set. So before we start, we need to again establish what the legal status of a substance is, because this impacts the spiking concentrations we need, i.e. the level of interest. So just as a reminder, if we're talking about authorized substances, then the MRL is used as the reference for any validation. Regarding unauthorized substances, we use the value of the RPA if it's available. Where we have other unauthorized substance, they need to be validated based upon the lowest calibrated level concept, the LCL. And this means they should be validated for concentrations which are as low as reasonably achievable. And we can use the minimum method performance requirement values from the EURL guidance document as an aid to this validation. When we look at this in a tabular form, we can see that we have to spike at 3 different concentrations, 3 levels, if you like. For authorized substances, we need to spike at 0.1 times the MRL, 1 times the MRL, and 1.5 times the MRL. If for some reason we're not able to get down as low as 0.1 times the MRL, the regulation does allow for somewhere between 0.1 and 0.5 times the MRL. For banned substances, unauthorized substances that have a reference point of action, then we use the reference point of action as the reference point. So 0.5, 1, and 1.5 times the reference point of action. And unauthorized substances without a reference point of action, then we have this lowest calibrated level. And again, if we've got an MMPL value as a reference point, then that's very helpful to us. We're now going to work through an example of a validation batch for confirmation methodology with an authorized substance. In this particular case, we're going to focus on a macrolide. And this particular macrolide is going to validating for this particular macrolide in porcine muscle, and it has an MRL of 50 micrograms per kilogram. This approach to confirmation is based around the analysis of a series of batches of spike samples over 3 days. This particular suggested scheme is based upon using matrix match standards, so we need to correct for recovery prior to any calculations of trueness and precision. When we do correct for recovery, when the requirements of trueness are fulfilled, a fixed correction factor may be used. Otherwise, the recovery factor obtained from that specific batch shall be used to correct for recovery. At least 6 replicate test portions of a single blank sample need to be spiked at 0.1, 1, and 1.5 times the MRL. So this is the change from the previous decision, where you were allowed to spike at 0.5, 1, and 1.5 times the MRL. On the first day, we prepare calibration standards, matrix match standards in the pork extract of a blank at 0 and a relevant concentration range for the measurements required in the spikes. And we chose this particular occasion to use 7 replicates, so 1 more than the bare minimum, spiked at the 0.1 times MRL, 1 times the MRL, and 1.5 times the MRL. After that batch is prepared, then it was analyzed. And then on day 2, we repeat the process. So prepare calibrants and prepare the spikes in exactly the same way as day 1, and then analyze them. And then on day 3, the same again. Before we go into detail about the actual validation, let's just quickly look at some of the raw data from the method. So this is a chromatogram of a matrix match standard at the different MRLs showing all 18 macrolides. And then these are some typical calibration graphs formed from the analysis of the matrix match standards using bracketed calibration. You can see that the residuals and the R-squared coefficient of determination are fine. The first calculation we're going to look at is for trueness. So trueness is expressed as the mean of the recovery corrected concentrations, because in this experiment we have no internal standard and we're using matrix match calibration. So if we look at 50 micrograms per kilogram as an example of the MRL, we basically have 7 replicates over 3 days. So each of these values. Each of these values has already been corrected for recovery. So the next step we have to do is to create the mean of all the measured recovery values divided by the spiking concentration. And if we do this, we get a value of trueness as 100.4%. And then we need to repeat for each of the other concentrations. So the next set of calculations I'd like to look at are for repeatability. So this is the same data set as we saw before. So this is 50 micrograms per kilogram, 7 replicates over 3 days. And the first parameter we want to calculate is the within day variance. And this is the mean of the standard deviation for the values each day after they've been squared. So these are the values each day. And so this is the variance within day. The next parameter is the standard deviation within the day. And this is equal to the square root of that within day variance, as we see here. The third value is the repeatability expressed as RSD, and this was equal to the standard deviation within the day divided by the total variance that we see in the table. And we do that, we get this value here. And then lastly, but not least, the repeatability value as shown on the screen. Third set of calculations are for the within laboratory reproducibility. So same data set as we saw before. And the first parameter we want to have a look at is the total standard deviation. And this is equal to the standard deviation of the total variance. So standard deviation of all these values here. We can also then express that as an RSD value by dividing that by the total variance that we see in the table. And then also we can also calculate the within laboratory reproducibility. And lastly, we're going to move on to calculation of CC alpha for MRL substances. There are a number of methods available now, but I'm going to focus initially just on a conventional graphical approach. So the idea is we plot the values for each of the measured recovery corrected concentrations from the analysis of each of the replicate spikes. So at 0.1, 1 and 1.5 times the MRL against the expected spiked values, and then we fit a regression line. We also then plot regression lines for the data plus the reproducibility as we calculated earlier on, and then minus the reproducibility. This slide shows what the graph would look like. So we've got the measured concentrations on the y-axis, and we've got the spike concentrations on the x-axis. And here I've just displayed the mean values for simplicity. And then we have a series of regression lines through the data. So we have the black line here is the regression line for the mean, and then we plot a regression line plus the standard reproducibility of the data and a regression line minus the reproducibility of the data. At a confidence level of 95%, which is what we need for authorized substances, this gives a so-called coverage or K factor of 1.64 for a one-tailed distribution, hence the value 1.64 in the equation. We can use this equation to calculate CC alpha, and then we can derive these parameters from the graph. So the YC is the corresponding concentration at the y-intercept of the regression line plus the reproducibility. So if we take the regression line with the reproducibility and we look for where it intercepts, we get YC. B is the intercept of the regression line, and A is the slope of the regression line. However, it's a lot simpler these days to do these sorts of calculations on a spreadsheet. So we want to calculate YC, and it's the slope of the regression line plus the reproducibility times the MRL, which is 50 micrograms per kilogram, plus the intercept of that regression line. So we take the slope of the regression line plus the standard deviation, we take the 50 micrograms per kilogram, and we take the intercept of that regression line. We do that calculation and we find that YC equals 54.9. And as a reminder, it's this formula that we're trying to use to calculate CC alpha. So we've already calculated the YC, so now we need to calculate the B and the A. And the B is the intercept of the regression line and the A is the slope of the regression line. So we can use the spreadsheet to calculate the intercept and then the slope. And when we put all of the numbers into the equation, we end up with a value for CC alpha of 54.3 micrograms per kilogram. This slide shows the main results from the validation. For trueness, we should be within a range 80 to 110% at these concentrations, and we can see from the measured values, the calculated values, that we are within that range. We can then also look at our reproducibility values, which have to be within this range, and we can see the measured values again are within the range. And then from the reproducibility, we can extrapolate back to our repeatability values. And again, we are well within the acceptable limits for repeatability. And then our CC alpha value is greater than the MRL as it's supposed to be, greater than 50 micrograms per kilogram, but should be as close as possible to my 50 micrograms per kilogram. So now we'll turn to validation of a banned substance. So quantitative confirmation method for chloramphenicol in shrimp. So similar approach to what I described earlier. So analyze a series of validation batches over 3 days. This particular case, each batch has at least 6 replicate test portions of a single blank sample spiked, but this time it's 0.5, 1 times and 1.5 times the reference point of action. And just a reminder, chloramphenicol will have a reference point of action of 0.15 micrograms per kilogram. This suggested scheme is based around using matrix match standards, but also an internal standard, so recovery correction is not required for the spikes. So validation, day 1, set a calibration standards matrix with internal standards to cover the range that we need to quantify. And then 6 samples spiked at 0.075, 6 at 0.15, and 6 at 0.225 micrograms per kilogram. So on day 2, we repeat the experiments and then we analyze the samples. And then we carry out the same experiments again on day 3. We calculate the trueness and the various precision, repeatability, and reproducibility as before. So we have our repeatability expressed as an RSD R here for the 3 different concentrations. We have our within laboratory reproducibility expressed as an RSD for the 3 concentrations, and then we have the trueness values for the 3 concentrations. When we're looking at CC alpha for banned substances, we just need to create one regression line. So we basically plot the concentrations from the added concentration, the spike concentration, if you like, against the measured concentration over the 3 levels, and then we create this firm regression line. To calculate CC alpha for banned substances, we use the same equation as before, but in this case, the YC value is the intercept of the regression line plus 2.33 times the standard error of the within the laboratory reproducibility of the intercept. The K factor that we use this time is, instead of being 1.64, is 2.33 because we have an alpha value of 1% rather than the 5% previously. As in the previous example though, it's a lot easier to calculate CC alpha for banned substances using a spreadsheet. So the YC is the intercept of the regression line plus the 2.33, which is the K factor, times the standard error of the within laboratory reproducibility of the intercept. So YC equals, in this case, 0.018. And then we can calculate the CC alpha using the same equation as previously. So we actually have the YC value minus the intercept over the slope, and that gives us our CC alpha value of 0.020 micrograms per kilogram. This is a summary of the main results from the validation for a confirmatory method for chloramphenicol in shrimp. So the first thing to note is the values for trueness, within laboratory reproducibility and repeatability are slightly different to the previous example, because here we're working at much lower concentrations. However, it's quite clear to see from the slide that our measured trueness, reproducibility and repeatability values are well within the acceptable tolerances. The calculated CC alpha is shown at 0.021 micrograms per kilogram, again well below the RPA value of 0.15 micrograms per kilogram. In summary, Method validation, as a reminder, is the process of proving that an analytical method is acceptable for its intended purpose. Commission Implementing Regulation 2021-808 focuses on single laboratory in-house validation, as we have seen. The method characteristics that need to be verified vary depending on the type of method. So here we've focused purely on confirmation. We can assess calibration graphs and calculate trueness, repeatability, reproducibility, and the CC alpha value from a single validation set. But I would advise you to look at other experiments separately. And validation design is the same for both approved and banned substances, but the level of interest and the interpretation of the CC alpha value differs, as I've shown you. And that brings us to the end of this module. I hope you found it useful. I would encourage you to practice validation for confirmatory methods and also to practice the calculations that are required to generate the values needed. Best of luck.
Coming up next on GFoRSS TV.
Hi, my name is Simon Hurd, and welcome to our next training session on Commission Implementing Regulation 2021-808. And today we're going to focus on validation of a screening method. So after an introduction to screening and why screening is important, we're then going to talk about detection capability for screening, CC beta, which is probably the most important parameter we need to validate for a screening method. We're going to describe then some of the categories of suitable screening methods. And then we're going to go into a bit more detail about validation of a semi-quantitative screening method before we summarize. So let's have a look at why screening is important. So I'm going to use the results of a national residue monitoring plan across the European Union in 2020 as an example. And we can see the number of tested samples reported for residues, but also you can see that the non-compliance rate is very, very low. Only 0.3% of samples tested were non-compliant, and this is a feature of the survey year on, year out. So it makes sense in this case where we've got a very, very low level of non-compliance to use a two-tiered approach to analysis. We use a relatively low cost approach to screening first for as many samples as possible, and then we confirm any suspects positives. So it is important to recognize, though, that this screening confirmation approach only really is viable in these circumstances. If you're working in a situation where you're expecting residues to quantify whether they be compliant or non-compliant, then clearly a screening then confirmatory approach may not make much sense to you. Screening methods are designed and used to sift large numbers of samples for potentially non-compliance in a cost-effective but accurate manner. And Commission Implementing Regulation 2021-808 actually defines a screening method as a method that is used for screening of a substance or class of substances at the level of interest. And then a case of a suspect non-compliant result, analysis is repeating using a validated confirmatory method. So as I said in the previous slide, this approach is only practical when non-compliance is very low. Performance criteria for validation of screening methods weren't really described in any detail in the original decision 657, so there was a protocol devised by the European Union reference laboratories at the time to supplement this decision and actually gave a lot of useful details. Now, of course, we're talking about Commission Implementing Regulation 2021-808, and there are updated instructions and information now provided. However, there will be some revised guidelines to help you implement these instructions from the European Union on screening, which will be due later on this year. The most critical parameter that we need to consider when we're talking about screening methods is detection capability. And throughout this presentation, I will refer to this as detection capability for screening CC beta, because the concept has changed considerably since the previous decision. Detection capability of screening means that the smallest content of the analyte that may be detected or quantified in a sample with an error probability of beta. And in both cases, where we're talking about banned substances or approved substances, the beta error is actually 5%. So screening methods really has to be specifically designed to avoid false non-compliant results, or false negatives if you like. It's also important though to have a method that has a low frequency of false positives, because if you have loads and loads of false positives in your screening method, then the method will prove to be impractical. So what does CC beta then mean to our level of interest? So the CC beta shall be determined by suitable validation of screening methods, and we're going to show you this later on. For prohibited or unauthorized substances, the CC beta shall be as low as reasonably achievable. It's not that surprising given that these are banned substances. But in any case, lower than the reference point of action, as any reference point of action that is established. For authorized substances, for MRL substances, the CC beta shall be lower than the MRL, or in some cases the maximum limit. And this is different to previous. This slide shows the relationship between the level of interest and the CC beta for screening methods. So in a situation where we have our MRL substance, the CC beta will always be less than the MRL, and it's that value that we are using then to screen negative. From the point of view of bad substances though, again, the CC beta shall be lower, but as close as possible to the reference point of action. When we look at suitable categories for screening methods, the regulation states that a qualitative, semi-quantitative or quantitative methods can be used as screening methods, and it actually gives some indication of different validation requirements. It doesn't really go into a huge amount of detail as to what types of methods are appropriate, and I hope we'll see more of this in the appropriate guidelines that follow. The critical thing to note though is only those analytical methods which have been validated shall have and shown to have a false compliant rate lower than or equal to the 5% beta error shall be used for screening purposes. So whichever methodology you choose, you must make sure it is validated appropriately. Some of the most commonly used and effective screening methods are based upon things like microbial growth inhibition, receptor binding and enzymatic colorimetric assays, or immunological techniques in various formats. These are very cost effective and they are deployable, which is of interest because not all analysis needs to be done in the laboratory. In some cases, there is a need to actually test a lot closer to the point of production. So for example, in the dairy industry, they are capable of screening a large number of samples, but they are not without some issues. Each kit is very, very specific. So by that, I mean it is designed for a specific analyte or a group of analytes, and it's to be used for the analysis of a specific sample type. So it might be, for example, designed for a certain group of antibiotics in a milk sample or something like that. It doesn't provide much information about the identity of the substance. Many of these kits are actually based upon some sort of biological activity. Now, this doesn't really matter so much for screening as long as they're validated appropriately. However, if we have to be careful to use these kits within the recommended scope. If you apply a kit that's designed for a certain scenario into a different scenario, because that's what you need, then you may find issues with false negatives and false positives. Hence, again, this important thing to stress that these kits need to be validated for the use that you need. One example of antimicrobial inhibition test is the PREMI test. So in this particular type of kit, the extract is incubated in an ampule containing a strain of bacillus, which is held in a solid agar medium. If any samples that don't contain any residues, any blank samples, will change color from purple to yellow over a period of time. This color change is related to change of pH caused by the microbial growth. So after 2 to 4 hours, depending on the different type of sample, the color is checked. At this point, any samples that have failed to change color are suspected to contain antimicrobial substances, as the growth of the strain has been inhibited. Any suspect positives from this approach would then be confirmed by analysis using a validated LC-MS system. Again, with many of these types of kits, it's important to check the scope because they're not compatible for all antibiotics or all different sample types. HPLC with some form of optical detector is also a common choice for suitable screening methods, especially to cover the classes of analytes or matrix combinations that are beyond the scope of some of the biological or biochemical methods referred to previously. Fluorescence detection is very popular. It can be more sensitive and specific than a UV detector in HPLC. Of course, you need the analyte to fluoresce naturally, but sometimes if they don't fluoresce, we can derivatize them to make sure they fluoresce. Use of optical detectors, though, does rely on some sort of selective cleanup, typically using solid phase extraction. But again, not so much of a problem if we're interested in a specific analyte or a group of analytes with very similar physicochemical properties. And we can use chromatographic screening either in a qualitative way, so we're just simply looking for the presence or absence of peaks, or we can actually use it in a semi-quantitative manner where we have standards available. Another option growing in popularity for screening is actually to use LCMS-MS. Now, LCMS-MS comes into its own when we wish to extend the scope of the analytes for screening to many different analytes from different classes in various matrices. It is essential to develop and maintain performance that avoids false negatives like any other screening technique. We have a choice. Most screening workflows probably still focus on a targeted approach, looking for known substances at predetermined concentrations. But untargeted approaches using high-resolution mass spectrometry are becoming much more popular. Interestingly, with LCMS-MS, we can actually use the same method for confirmation, i.e. the repeat analysis. However, there's only the case if we validate for that purpose, i.e. for confirmation, and that the relevant analytical quality control acceptance criteria are met. So LCMS-MS provides us with a lot more flexibility in using the tool for both screening and confirmation. When we look at the characteristics of screening methods that we need to check performance at validation, it's quite different to the confirmation analysis. There are less parameters that need to be checked. So we don't need to look at trueness, we don't need to look at matrix effect or recovery. We don't really need to look at precision, as you can see here, as long as we assess the false compliance rate. What we're looking at basically, whether it be a qualitative, semi-quantitative or quantitative test, is selectivity, ruggedness, stability, and then the CC beta value. And we're going to focus really for the rest of this presentation on what I'm going to call semi-quantitative screening. So the first topic is ruggedness. Now, we covered this in a previous training module, so I'm only going to cover this again quite briefly. So in the same way as we looked at confirmatory analysis, in screening methods, it's all about introducing small changes to the experimental conditions. So this actually might include different sample conditions, but also minor changes in the analytical method that might occur during routine testing. And the idea is to actually document and to evaluate where any of these small changes have a significant effect on the performance of the assay. The regulation does not provide any details of acceptance criteria, it just says you have to check for ruggedness. And then the second thing that is the same again we saw for confirmation is stability. And again, I'm not going to go into a huge amount of detail in this. The stability of various aspects, the calibration standard, any matrix match standards, any spike standards, or any of the analytes or in the matrix needs to be checked during storage or analysis. And again, the document does give some details, but again, we covered this earlier on. So we saw how we looked at selectivity for confirmatory methods earlier in the programs. Selectivity is defined as the ability of a method to distinguish between the analyte being measured and other substances. And we can look at a conventional approach as we did before, or probably more relevant to a screening technique, we could focus on assessing the false positive rate. And then also, lastly but not least, the detection capability for screening CC beta. So the proposals I'm going to talk about for the rest of this presentation really are based upon the interpretation of the instructions in the new implementing regulation, but due to the absence of any current guidance document, I've had to use the 2010 guidance document. The main goal when we evaluate selectivity is to verify whether anything in the sample, for example, any co-extractives, natural materials, natural compounds, or in some cases any other analytes that are in our method could interfere with the determination of the target analyte. And we've described this before, that there are two simple approaches. The first thing is to look at analyzing an appropriate number of representative blank samples so that we're checking for any interferences on our analytes of interest coming from co-extractives from the blanks. And secondly is to have a look at other substances that may interfere with. So for example, if we're looking at sulfonamides, then perhaps one of the other sulfonamides might interfere with the determination of the sulfonamide of interest. Bear in mind though, if we're looking at screening from the point of view of methods with biological activity, then you need to design these experiments properly. It's probably why it's, from the point of view of screening methodologies, it's better to evaluate selectivity in terms of false positive rate. The 2010 guidelines document on screening methods provides some information about determination of selectivity for screening. It can be determined by the investigation of the responses from a series of blank samples to calculate a threshold value from which we can determine the false positive rate. Threshold value is defined as a value corresponding to the minimum analytical response above which the sample will be truly considered as positive. And this parameter is determined by looking at the responses from the analysis of 20 different blank samples from different origins, and it's calculated using the equation that you can see on the slide. So the threshold value equals the mean of those responses from the blank plus the standard deviation of those measurements multiplied by the k factor of 1.64. There is no acceptance criteria specified in Commission Implementing Regulation 2021-808 for selectivity, but as a rule of thumb, I would look at false positive rate of less than or equal to 5%, where at least 95% of the blank samples would have to give a negative result. So the response or the signal or the concentration will be less than or equal to the threshold value. And as usual with these things, it's a lot easier to actually see this in a graph. So here we have the measurements of measured concentration by LC-MS in this particular case of peaks that are same retention time on the same MRM as our analyte from 20 different samples of, for example, beef muscle. So we have a very low measurement here and we have quite a relatively high measurement here. And so what we're doing is basically looking at the mean of those values, which is the line across here we see, and then the standard deviation, and then we add that standard deviation to the mean to get our threshold value. And we can see in this particular case, we have a single value that actually exceeds the threshold value. And one value out of the 20 is enough to still give us our 5% false positive, or less than or equal to 5% false positive rate. Commission Implementing Regulation 2021-808 provides three methods for the calculation of detection capability for screening CC-beta. All of these methods are based upon the evaluation of the response from blank representative samples spiked at various concentrations. The methods vary in the way that the spiking is carried out and the way that the data is interpreted. First thing to note is the samples used should be representative of the commodity or tissue species from multiple sources. They should not be replicates from the same single sample. The idea behind this is to try to introduce as much natural variability as we can into the assessment. It's also important to validate the method for all the analytes that you're looking for and also across the individual matrices of interest. So if you're validating a set of vet drugs in muscle and in liver and in urine, you need to validate this separately because those tissue samples behave very differently. It is possible to combine or consider combining multiple species, but initially when you're first carrying out your first validation exercise, I would again keep these separate, so that you can understand the analytical characteristics for each of the species. If they prove to be very similar, then in future you could combine them into a single validation experiment. Another important term used when referring to a screening method is screening target concentration, STC for short. Screening target concentration is defined as the concentration lower than or equal to the CC-beta at which a screening measurement in a routine analysis categorizes the sample as potentially non-compliant and triggers a confirmatory test. So you can think about the STC as being the spiking level for a screening method. For authorized substances, the STC must be less than or equal to the MRL, but really the desired STC for ML compounds should be looking at sort of half the MRL where possible. For banned substances, the STC needs to be at least lower than or equal to the RPA, but really they need to be as low as possible. First method outlined in the regulation for calculating detection capability for screening CC-beta uses the calibration curve procedure that we are familiar with through our work on confirmatory analysis. So this is based upon plotting the measured response against the added concentration from an analysis of a series of spikes. For authorized substances, we spike at and below the permitted limits, starting from the desired STC in equidistant steps. And for banned substances, we spike at or below the RPA, again in equidistant steps. In both cases, the CC-beta will be the corresponding concentration at the spiking level plus 1.64 times the standard deviation of the within laboratory reproducibility of the mean measured content at the STC. If we use this approach, then the CC-beta is greater than the STC value. The second method in the document is based upon the investigation of a series of replicates, blank samples, spiked at the desired screening target concentration, from which we then calculate the cutoff factor and then the false negative rate. The cutoff factor is the response from a screening test which indicates that the sample contained an analyte at or above the spiking level. For this particular approach, the established CC-beta will equal the screening target concentration, as we will see. So in terms of numbers of samples required for this approach, it depends upon the spiking level used. In our case that I'm going to show you here, the screening target concentration was always less than or equal to 50% of the MRL. So we used 20 samples. And then our assessment rate is that only one of those 20 samples can be shown to be a false negative. The third method outlined in the regulation is the use of standard measurement uncertainty to calculate CC-beta. It gives you a little bit of information about using the K factor of 1.64 or alternatively a t-distribution, and it talks about the within laboratory reproducibility and the trueness are suitable to define the measurement uncertainty. But there isn't really any other information, any other guidance. So I'm hoping that in the new guidelines that are going to be published by the European Union reference laboratories later on this year, that we're going to see some examples of how methods 1 and methods 3 are actually applied to calculate detection capability for screening. Before we go on then to have a look at a little bit more detail about how we use method 2 to calculate CC-beta from a screening experiment, just wanted to show you an example of a large scope multi-residue method for screening of vet drugs in a range of different tissues using LC-MS. And the key thing is we have to have some sort of generic extraction conditions. And here you notice the use of acetonitrile, but instead of formic acid, we're using oxalic acid, which will help us mitigate any issues with chelation of tetracyclines, for example. We add a salt and then we shake, and basically all our hopefully all our vet drugs have gone into our supernatant and our acetonitrile. However, there will be a lot of other co-extractives that will have also gone into the acetonitrile, so we have to have some simple cleanup. And what we're using here is a dispersive SPE step. So basically we have an absorbent, we based upon C18 material, we shake our extract with the sorbent, and hopefully most of our co-extractives stick to the sorbent, and hopefully most of our vet drugs are transferred through. And then we have another centrifuge step to separate liquid from solid before carrying out the LC-MS. And if you want, there's more details you can see in this link given. So the guidelines of 2010 give two approaches for calculating the cutoff factor, and this is the most simplistic one. I'll go through this first before moving on to a more statistical based approach, which I would recommend. So here we can see the responses or the calculated concentrations for all our blanks, our 20 blanks, and then we can see similarly the measured concentration in our spikes. And what we're doing here is evaluating the range of analytical responses for the blank samples and for the spike samples. We select the lowest response in the spike samples. And this then is the cutoff factor, provided that the lowest response for the spike samples does not overlap with the highest response for the blanks, which is the case we can see here. The second approach to calculation of the cutoff factor in the guidelines from 2010 is the statistical approach, which takes into account the beta error of 5% that we've talked about before. So here rather than taking a single dot, we're actually going to be doing a calculation in which will then generate this blue line, which is our cutoff factor. So the cutoff factor is still the response from the screening test, which indicates that a sample contains an analyte at or above the spiking level. The data that I showed you is the same data as we saw earlier on from the analysis of 20 blank samples spiked at a desired STC. And in this case, the spikes were made at concentrations of half the MRLs. And the response is determined, the calculated concentrations for each analyte using the primary MRM transition. And then we can calculate the cutoff factor using the following equation. So the cutoff factor in this particular case is equal to the mean of the responses in all the spikes minus 1.6 times the standard deviation of each of those analytes in the spikes. Here we have an example of some screening results from validation of ciprofloxacin at an STC of 0.1 micrograms per kilogram. So you can see here the green spots give us the responses of all of the spike samples at 0.1 micrograms per kilograms, and then we have the yellow spots here, which are the responses of equivalent in the blank prior to spiking. And the first thing that you can see is that there is some overlap between the two, the spiking and the blanks. But also when you start looking closely, you can see that actually the cutoff factor here is extremely low, and therefore there are some spiked values actually that sit below that cutoff value, so that we have more than one false negative result. Commission implementing Regulation 2021-808 states that the concentration level, i.e. the STC, where only less than or equal to 5% false compliant results, false negative results, remain, equals the detection capability CC beta of the method. In our case, we had 20 spike samples, so the concentration of which there are less than or equal to one false compliant result out of those 20 samples. If the results fail this requirement, as we saw in the previous slide, then we need to go back and increase the concentration of the STC and repeat the experiment until the result passes. So here we can see the results from the repeat validation where the STC is being spiked at 1 microgram per kilogram. So we can see the calculated concentrations in the blanks and in the spikes. The first thing we note is there's no overlap at the lowest response for the spike sample with the highest response of the blank samples. And only one of the spike samples has a result below the cutoff level. The STC at 1 microgram per kilogram then is where less than or equal to 5% of false compliant results would be present at the level of interest. And so STC at 1 microgram per kilogram is the detection capability for this analyte in this commodity by this method. So the CC beta established, as you can see, at 1 microgram per kilogram is well below the MRL of 100 microgram per kilogram for this particular commodity and analyte combination. For official control, if we were setting up this validation experiment, we would be better off setting the STC at half the MRL, i.e. 50 microgram per kilogram. This work was to investigate the sensitivity of the method. Before we conclude, I thought we would show a summary of the terms used in this validation for screening methods. So the first term that we looked at was the threshold value, and this was to help us look at selectivity in the terms of false positive rates. And the threshold factor was determined through looking at the mean of our blank measurements plus the standard deviation times the K factor of 1.64 to give us this threshold value. When we look at the cutoff value, then again, similar approach, but we took the measurements around the STC, the actual STC minus the standard deviation times that K factor of 1.64, which gave us our cutoff value from which we could determine the false negative rate. And as we can see in this graphic, the different methods give us different relationships between CC beta and STC. In our case, we were looking at method 2. So in fact, CC beta equals STC. So the CC beta would be the same value as the STC. Screening tests are designed to detect the presence of an analyte or a class of analytes at a level of interest, and they are characterized in certain ways. It's very important for a screening test to be successful. It has the capability for high sample throughput. In many cases, it needs to be cost effective and it needs to be simple to perform, especially if it's going to be used away from the laboratory in a deployable form. The goal is to detect potentially non-compliant samples in an effective manner. So we need to make sure that we avoid false negative results, i.e. a screening test cannot miss any non-compliant samples. And many screening tests are often based upon information from biological activity, which is fine for screening, but it's not providing information on structure. Multi-residue methods based upon LC-MS or LC high-resolution mass spectrometry are an effective approach to screen many compounds in a wide variety of samples. So if you're interested in multi-residue screening, then these types of technologies, albeit not necessarily simple to perform or cheap, are certainly a cost-effective way of actually obtaining many results from many analytes in lots of different commodities. The interesting thing also is that the same method can be used for confirmatory repeat analysis if it has been validated for that purpose. As with confirmatory tests that we saw previously, screening tests must also be adequately validated for each of the analytes of interest in the relevant matrix. But as we've shown, the parameters to be determined for screening are more limited. So we need to assess the ruggedness, the stability, the selectivity, and the detection capability for screening. The detection capability for screening, CC-beta as a reminder, is the smallest content of the analyte that may be detected or quantified in a sample with an error probability of beta, which in this case was 5%. The screening target concentration, STC, is the concentration lower than or equal to the CC-beta at which a screening measurement categorizes the sample as potentially non-compliant and triggers a confirmatory test. And lastly, the value for CC-beta is greater than or equal to the STC, depending on which approach you took. And that brings us to the end of this module, looking at validation for screening methods. I hope you found it useful.
You are watching GFoRSS TV. Today, on GFoRSS TV.
The Global Food Regulatory Science Society. GFoRSS mission includes knowledge generation and dissemination, underpinning food regulatory decisions, in support of food control systems, Our interventions focus on promoting food regulatory scientific disciplines. Consistent reliance on food regulatory sciences enables robust food control programs. Contributing to more resilient food systems, and a safe, accessible, abundant and nutritious food supply.
Thank you for watching GFoRSS TV.